Hello again, Internet. Touring the streets off the beaten path a little bit. Still historic district and fancy, but not as much street light, not as many people. And thought I'd do another ramble, but I'm going to start to make these rambles maybe useful information instead of my original ramble. So, with that goal in mind, I want to talk about stepper motors. Now, stepper motor is a DC motor that is designed to step instead of rotate. So, normal motor, you connect it to power, and it speeds up to top speed, and it just stays there until you disconnect power. In theory, you can use motor controllers or maybe even resistors to control the speed of the motor. But if you want to control exactly where it stops, that's not really an option. If you want to control to make it not rotate, or when it stops at a given spot to make it not rotate away from there, not really an option. So that's one place where a stepper motor can come in real handy. So a stepper motor will have 200 or 400 or 160, depending on who's making it and the size and various other things. You'll have these steps. So a real common size is a 200 step motor. You see that all the time. So basically you tell this motor to step in one direction or another, and it moves 1/200th of a turn. And that's how they worked for a while. But someone figured out eventually that you can do what's called micro stepping. So now that 200 step motor, if you use 2x micro stepping, or double micro stepping, now that can stop 400 different places. Or you might go to 4x or 8x, 16x, maybe all the way up to 256x, to the point where you've got incredibly fine resolution out of a motor that's relatively fine resolution to begin with. Now you're talking about insane resolutions. So that's a nice feature. That's the main feature, is that it's very precise, and once you get it to a spot, it can also hold itself there. So if you're trying to twist it by hand, you probably won't be able to do that. It's going to be stronger than your ability to twist by hand. If you used a tool, you can probably overcome it, at least for a small motor. So there are a few standard sizes that most everyone uses. There's NEMA 14, which is 1.4 inches wide. Note that these motors are entirely metric, except for their names. So the NEMA 14, if you download a 3D model of it, everything's metric. The screw threads are metric. The shaft is metric. It's all metric. But the name of the size is based on the 1.4 inch body, which is actually a metric number that's approximately 1.4 inches. So it's kind of weird how that goes. Next size up is the NEMA 17, 1.7 inches. Then there's the NEMA 23, 2.3 inches. The NEMA 24, which is kind of an odd duck. It's 2.4 inches. This one's actually metric all the way, because its number is not 2.4 inches converted to metric. It's something else converted to inches, and it's about 2.4 inches. And everything about that motor is metric, whereas the NEMA 23 is very clearly using inches for everything except for screw threads. And maybe shaft size, but shaft size can change depending on what the customer and manufacturer want to do. So it's kind of odd, and you'd think the NEMA 24 would be more popular because of that, because, you know, a very small proportion of the world's engineers are using inches, especially in robotics. In the United States, in robotics, you don't use inches very much, or if you do, it's converted. So it's odd that the NEMA 23 took over, but kind of has, which means you can get more options which means you can get a better motor in a slightly smaller size, which means it's probably not going to go away anytime soon. So how do you control these motors? So you can't just connect like voltage straight to these motors like with a regular DC motor, because these will have 4 wires, sometimes more, but usually for what most hobbyists and stuff do, it's 4 wires. And these 4 wires go back to what's called a motor driver. It's a controller unit for the motor. And by energizing the 2 different coils that the 4 wires are connected to in the right order, they can make the motor rotate, they can make it stop where they want it to, and they can make it hold there. And that's what they could do many years ago already. They could also add micro-stepping, so common was 16 times micro-stepping. So you'd have a 200-step motor with 16x micro-stepping. Now you can stop at 3,200 individual spots around the rotation, which is pretty good. But downside, not very strong. If it gets stuck, it'll lose steps and you won't know about it, so the whole machine will be off and could cause all sorts of problems. And again, not super strong, not super fast, and makes a lot of heat compared to some other motor types anyway. So, over the years, people have been optimizing every part of this. So the motors themselves have gotten a lot more efficient, especially with hybrid stepper motors. You're getting a lot more performance with the same amount of heat or less in the same package size or less. So that's been really nice. But also, you've got the companies making the stepper motor drivers, specifically Trenamec. They make the TMC driver series, and those are kind of incredible because they've managed to make the motors run faster with more torque, quieter, making less heat, and they even detect or they can at least detect when the motor has stopped. So if it misses a step and it gets out of alignment, that could cause all sorts of problems. Rather than just letting it happen, now it goes, oh, the motor stopped. I need to do something about that, either fix it, add more steps to undo what was lost, or at the very least, alert the user, maybe cancel the operation so I don't cause a crash that could destroy the machine. In addition to that, there are also encoder motors, or motors with encoders built in, or also they have encoders that can be attached to motors, which will allow you to know if it in fact did miss a step. Again, that was super useful before the TMC drivers became standard. These days, less useful. They can be more useful for getting back on track if you figure out that something went wrong, but just the drivers are generally enough to tell you that something went wrong at this point, so you don't really need the encoders for that anymore. Although they can be a nice extra, just if you want to be extra sure. So let's see. Yeah, so the TMC drivers, they're mostly pretty small. They come on these little 16-pin circuit board packages. You plug them in. There's like a standard that everyone uses. Although sometimes people don't quite follow the standard, and that causes problems. But generally, people follow the standard. There's also a little card edge package version that Big Tree Tech has been trying to push, but I really don't think it's catching on, thankfully, because it's kind of not necessarily proprietary, but it's their own thing, and there's already a standard that works, and they're not really adding anything by making their new standard that is different. Which way to go? Try going up the hill. It's a nice little looks like a church, school, something, combination of the two. Alright, so covered the separate motors, covered the drivers. Bigger motors obviously need bigger drivers, or more powerful drivers anyway. You can get away with the small 16-pin package drivers up to some NEMA 23 motors, although even then you're going to be pushing it as far as thermal limits of the driver. But they make bigger drivers that, you know, instead of being the size of a finger, it's the size of a whole hand. Those can drive a lot more, and of course they go up from there. The biggest step motors are downright huge. And let's see. So I covered the motor, covered the drivers, connecting them. Simple way, connect power and ground. And you want logic power as well. So you'd want like 24 volt and ground. It's the actual motive force power that's going to use to drive everything. Then you might send over 5 volt or 3.3 volt as the logic power. And that'll be extremely low current stuff. Then you also need to send over a wire, the direction pin wire. So if you set that to ground, it's one direction. Set it to 5 volt to 3.3 volt, it goes the other direction. Then you've got the step pin, which you need to send over signal going high, and then waiting for a certain amount of time, not very long, like tiny fraction of a second, and then back down again. They call that a pulse, and then the motor moves one step. Trinamax get a lot more complicated because now you can use serial commode to connect for diagnostics and feedback, telling you, oh, I missed a step, or I'm overheating, something like that. And so that's 2 extra wires plus a bunch of coding that gets involved. It's useful, it's just a lot more work. And let's see, and there's usually an enable pin, but you can just like leave that connected all the time if you want. It runs a little bit warmer, but whatever, usually not a problem. And yeah, that's about it. Trying to think if there's anything else important. I will give a little preview. Well, no, I won't. I'll do the next video next time. All right, so thanks for watching or listening to me ramble, and catch you next time. Thanks for watching. Goodbye, Internet.